All right. In this video, we are going to derive a heat diffusivity equation for cylindrical coordinates by using heat diffusion. No, no, no. In this video, we are going to be deriving a heat diffusivity equation of cylindrical coordinates by using differential energy balance equations. So, we have a system here where we have a cylinder that is extending across the z-axis and has an x and y coordinate. So the way that we're going to break this down is we're going to solve for the energy stored and how this is equal to energy balance our energy generation and equal to a net heat flow for the system. So we're going to be using this by setting up polar coordinates for our system. And we're going to examine this with the X and Y grid. So if I set up a little X versus Y diagram, the way that we're going to visualize this is what we're going to use polar coordinates across just a slice of this cylinder to kind of look at what the overall energy storage and net heat flow and energy generation would look like for a system like this. So the reason why we take individual slices out of the cylinder rather than just doing the whole cylinder is really just to make our lives easier. If we took every part of this pipe and tried analyzing it all at once, the math for it would be pretty lethargic. And even if you took individual circles of every part of the cylinder, you start running into problems where, let's say, we have a pipe of water flowing through and it's only about halfway full across our system. Well, what can happen with that is when we have the water that's in contact with that part of the pipe being halfway full, that's interacting with it via convection. That's heating the pipe via convection. And the other half of it would be heated up by conduction by proxy of the heated bottom part. So immediately you can kind of see the problem with where you try to analyze all of this, you're dealing with two different systems at once. So it makes sense for us to kind of simplify and break this down by just taking individual slices of the pipe. So let's go ahead and do that. So this is me, let's say I'm taking like this slice of it, right? And move that over there. So I'm going to have some little slice that looks like this. And we're going to try to we're going to try to express this in differential equations. So I'm going to have our arc length, and we're going to have our change of radius happening just beyond it. We're going to make a little system that looks like this. So this is the energy balance with the change of our heat flow coming into this. So I'm just going to make a little shaded system and we're going to label this. So we're going to label our entire system now. So we have our radius and over in this change of area, we're going to have our change of radius, right? For our angle, we're going to call this delta. Yeah, we're going to call this delta. And we're going to call this side over here uh, delta theta. However, it's more than just delta theta. In this case, this is also the change of R as well across our system. So this is actually R delta, and this is R delta theta in this case, because it's our change of radius. And we have to consider that this is just a slice of it from the bottom. If we're actually making the whole cylinder, if I were to make this three-dimensional, right? We also have to consider change of Z as well. And that kind of gives us a more three-dimensional analysis of this, which is going to be important when we begin to analyze the net heat flow of this system, when we're considering where heat is coming from. So, or I should also put that this is also just Z. So we kind of have a diagram for our system. So let's go ahead and start breaking down what individual parts of this heat diffusion equation are going to look like. So similar to other problems that we've done when we talk about diffusivity, is that when we talk about energy storage, we're trying to say, how do we translate heat into a type of energy, right? So the way that we do that is we have to consider the heat capacity. And if we're going to look at the units of this, this is a per volume basis, right? So we're going to say that this is our density times the heat capacity times a change of temperature over some change of time, right? This all makes sense in terms of units. We have our heat capacity, uh, which is some mass, or this, which is like some energy taken by mass per Kelvin, right? And so we multiply that by the density and the change of temperature to find the total energy that we can generate. However, we're still left with volume in this case. So if we look at our system, to make a three-dimensional analysis of our change, we can just multiply all the changes together. And when we do so, we get our change of theta times d of r times d of z. Okay, so this makes for a pretty easy energy storage equation, and this also makes sense. We can also say that, okay, this makes sense because we have a density that is being canceled out by a given volume, and that leaves us with the mass of it times the heat capacity times a change of temperature, which just leaves us with an energy that's being stored. That makes sense intuitively. So if we look at energy generation, this is a very similar type of rationale. We have the heat being generated in our system, and this is being multiplied by the change of volume that we have over here, which again we just said is a delta change of radius and a change of the z direction. So something I want to note here is that when we start looking for the net heat flow of this, the we're gonna try to find this term, the d of delta, d of theta, d of r, and d of z, to kind of have like terms across all of our equations. So I just want to kind of save that in our pocket for now as just something that we need to understand to intuitively break down what this heat diffusion equation is going to look like. So. I'm going to go ahead and just separate this. I'm going to look at net heat flow. Okay, so when we look at net heat flow, this is where this type of problem begins to differ compared to other net heat flows that we've looked at, because we're not just looking at this from a Cartesian standpoint where we just have one equation. This is three-dimensional. And so we have to consider it coming from the arc length, we have to consider it coming from the change of radius, and we have to consider it coming from our change of z. So how do we do this? I would say probably the easiest part would be starting with the heat flow coming from z, which uh using a Taylor series approximation again, because we're dealing with differential equations and we're approximating by linearizing and using a infinitesimal amount of small numbers to add together to find our change of heat over some period of time, we're going to have an equation, or I should say net. We're going to have our heat flow coming in from the z direction, kind of like this, and we're going to have it leaving our system. And if we're going to call this Q of z, we can say that this is Q of z plus the change of z that we've experienced. So this is d of z. And that is leaving our system. So we're going to subtract by this value. And as I was saying, we're going to use the Taylor series approximation here to give us our value here. D of z plus d of z, or q of z plus d of z, which is our heat flow of the z direction plus the change of the z direction, equals our, let's see here. This would be our heat float of Z plus the sensitivity, or we can imagine this as the change of Z in regards to the change of distance Z multiplied by that distance of d of Z. So when we plug this into this equation, we get something that looks like Q of Z minus Q of Z minus the sensitivity of Z over some distance multiplied by d of Z, which then just leaves us with the negative sensitivity of heat flow Z times the distance of Z equal our net heat flow of Z. So a lot of Q and Z there, but now what we can do is begin to apply Fourier's law to this, which states that our heat flow should equal some thermal conductivity times the area multiplied by some temperature gradient over our distance, which in this case, we're looking at d of z. So if we go ahead and plug this in, we can say that, oh, did I do something? I'm missing an equation, aren't I? No, we're fine. Sorry. We can say that, first off, we can cancel our negatives. We can say that d over d of z equals k multiplied by area multiplied by our temperature gradient of T over Z multiplied by D of Z. So, something to know. What is our area? Our our area in this case is the cross-sectional area that the heat flow is entering through. So if we observe this three-dimensional object, if we're coming from the Z in this case, Z coordinate, Q of Z, we're actually going to go through, I'm going to circle it here, this cross-sectional area. And if we look, this cross-sectional area is d of r multiplied by r change of theta. So in this case, area equals radius change of theta multiplied by change of radius. So that's our area. And this is where I get back to us pocketing this knowledge. This gives us our like term over here to relate this net heat flow for the z direction. So when I do this, I get d of z, k, multiplied by our change of temp, or just our temperature gradient, multiplied by r change of theta, multiplied by change of r, multiplied by change of z. And we're just going to leave this here for now. We're just going to call this our net flow of z, and we're going to move on to our net heat flow or heat flow, sorry, for the let's do the R direction. So we're gonna do it with change of R. So rather than going this way, we're instead gonna have our heat flow come in like this. We're gonna call this Q of R, QR plus D of R. Okay, so let's observe this. We have Q of R minus Q of R plus D of R. So this is our net heat flow for the R direction, right? Nets. So we're just going to do the same thing that we did for Q of Z over here. We're going to say that Q of R plus D of R equals Q of R plus our sensitivity, Q of R, over, in this case, it would be Q of, or no, sorry. This is change of Q of R over change of R multiplied by D of R, right? So knowing this, we know that our Q net equals negative change of Q of R over D of R multiplied by D of R. That is our Q net. right? So now we can kind of do the same thing that we did with Fourier's law earlier. We can say that, okay, Q of R equals negative K area multiplied by d of t over, in this case, this is change of temperature over the change of radius. That is our new temperature gradient. So that is going to be our difference. But if we sub that in, these become positive, and we have something that looks like, I'm going to shove our derivative out here. K times area multiplied by the change of temperature by the change of radius, which this is again multiplied by our change of radius. So again, we're going to try to find area here. Our cross-sectional area in this case is instead r change of theta multiplied by d of z. That is going to be our cross-sectional area at this point uh, for this one. So we're going to say the area equals r change of theta multiplied by, what did I just say? This is r delta theta multiplied by d of z. And here's something that we're going to do differently. We're not going to shove r out of our equation. What we're going to instead do is keep it in here, multiplied by r, multiplied by d of t over d of r, multiplied by d of r times d of z, multiplied by d of theta. The reason why is because we're looking at this from the derivative of r. So we actually have a lot of like terminology over here. And so for us, or I should say it behooves us to say, okay, we should probably keep the like terms together, and we're going to keep radius in here, which is going to help us express a more realistic differential equation for this, or heat diffusivity equation with this. So we're going to keep r in this equation. All right, and that leaves us with one more heat flow. And now we're going to consider the heat flow coming in from the change of theta. So we're going to be coming in like this. So one thing I want to establish immediately is when we use Fourier's law for change of theta, there actually is something a little strange that happens. If I were to do, let's say, K times change of temperature over change of theta, if I look at what happens with the units here, this is second, this is joules per meter Kelvin second, right? Yeah. And this is multiplied by our Kelvin, which cancels out our Kelvin later. But this is in radians. That's not right in this case. We don't have an expression for radians here. Our units don't actually align. So this can't be right. So what we're going to say is that Q theta equals K d of t over radius change of theta, as we've established with the arc length over here. And that is actually going to give us a realistic expression for our theta. I'm gonna shove this over here. So whenever we do Fourier's law, we're gonna do it like this instead. We're gonna have this division of radius because that helps rationalize our actual heat flow to make our units make sense in this case. So let's go ahead. Um, okay, let's start with finding our net heat flow for this direction. Again, same equation as earlier to find our change, I mean to find our net heat flow, or no, to find our heat flow that is leaving this direction, we're just going to add in regards to RD of theta. RD of theta, which in this case, this is just going to give us the same equation where R change of R, or R theta plus, no, 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 our heat flow. of theta plus our change of theta in regards to radius equals q theta plus our temperature sensitivity, some change of theta multiplied by change of theta, right? So let's go ahead. Uh, let's go ahead and proceed with this equation, which then of course leaves us with negative sensitivity, q of theta over d of theta multiplied by d of theta. And we're going to go ahead and sub this equation in. So we have change of theta multiplied by our new Boyer's law, which is k times d of t over r d of theta. So remember, we have this 1 over r, right? I'm not mistaking anything, right? Just making sure my equation looks right. Yes, okay. Just making sure. And then uh we're going to then multiply this by our area, which if we go back up here, the area, in this case, the cross-sectional area of this going into this three-dimensional shape is going to be our change of radius multiplied by our change of z. So I'm just going to rewrite this as change of r times change of z. And then we're going to set this to change of theta. And we're going to shove our like terms outside. So I'm actually going to rewrite this quite a bit. I'm going to say that d of theta, 1 over r, k, change of temperature in regards to change of theta, multiplied by d of r, d of z, and d of theta. Okay, so now that we have these uh, heat flow equations for all of our coordinates, this is going to be kind of the tedious part of shoving all of these equations together. So I'm going to see if I can copy and paste these equations over. Oh, that is not what I wanted. There we go. Apple technology is not impressing me. Okay, so our energy storage is going to be equal to our net heat flow plus our heat generation. So now we're just going to set all of the equations here. We're going to say d of z times thermal conductivity times the temperature gradient regards to d of z is equal to r d of theta by d of r multiplied by d of z. And this is going to be plus d of r multiplied by our thermal conductivity, multiplied by our radius, multiplied by our change of temperature in regards to a change of distance, multiplied by our changes. And then this is going to be plus d of theta, 1 over r, k d of t over d of theta, and dr d of z, and d of theta. Okay. And then we also have our generation term, which is plus q multiplied by r d of theta multiplied by our d of r multiplied by our d of z, so our volume. So now that we have it all together, we can kind of begin simplifying a lot of these expressions. So the hard work is done. Now it's just plugging it all together. So firstly, Let's go ahead and get rid of these volumetric terms. And we're also going to divide by r across all sides. So everywhere is being divided by r. Let's say that this is also divided by r. And we're going to go ahead and cancel out our like terms. And I'm going to put, there's an area where I don't want to put 1 over r, which I will explain in a second. I'm just going to put 1 over r. Okay, so the reason why I wanted to put 1 over r here, because you're probably looking at this and saying, well, why aren't we just canceling this r over here? The reason why is because that r is not equivalent to the r that we're dividing by. This is in a differential equation inside, and this is regards to a different equation completely outside. So we're going to actually keep two terms separate from each other, just for now while we make this equation. So, okay. We've made that, which is nice. The other thing that we can do is we can actually get our heat diffusivity constant by saying that our heat diffusivity constant equals K over some density and heat capacity, right? If we look, we have K here, and K here. And now the last thing I'm going to do to try to simplify this is I'm going to go ahead and shove these differential terms over here and just make them double thetas in this case. So I'm going to divide you by and heat capacity. So now that we have all of these simplifications, now what we can do is shove them together. We can say that, sorry, I just got a notification that my Zoom meeting's ending in 10 minutes. Apparently, this has been a very lengthy demonstration, but we have d of t over d of t. So our change of temperature over our change of time equals our diffusivity constant multiplied by this is our double derivative of temperature in regards to the z direction plus 1 over r multiplied by our double derivative of our temperature in regards to radius plus 1 over r squared, because this is already being divided by r, with a double derivative of temperature and change of theta. And then all we do is just add our heat generation or energy generation and divide it by our pressure and heat capacity. And this, so sorry. This gives us a heat diffusion equation using cylindrical coordinates. Right. Go ahead and make that pop up. Lindsay, okay. Okay, cool. Okay. Okay. In this video, we are going to be solving for a simple problem using the heat diffusivity equation that we have just extracted. We are going to assume that this is a steady state process that has no heat generation and also or no energy generation and also only has heat flow in the radial direction. So I want to give a quick addendum very quick. I said in the previous part that we take the derivative of the radial derivative and that we can apply it to this derivative. That is indeed not correct. These are two separate equations in this case, and we don't get a double derivative, so we just leave it as a single derivative multiplied by the radial derivative. So I just wanted to say that part is corrected in this. I drew this correctly, and I have all these crosses here because this is just kind of the assumptions and what we've been told. Steady state means that we have no accumulation, uh, we have no generation in the system, and we only have heat flow in the radial direction. We don't have any. for our heat flows for the Z or arc length. So just to kind of show what all of this is, I just wanted to save some time in writing this all. So what we're going to do is we're going to make a equivalent thermal resistance equation that is analogous to how circuits are analyzed and how their resistivity is analyzed. So the way that we're going to do this is we're just going to we're going to set this equal to zero because we're in steady state. We have no accumulation of material. So we set this equal to 1 over our derivative d of r by r d of t d of r. All right, so immediately we can cross off 1 over r because we're set to equal to 0. So we have r equals d over d of r dt d of r. And now something that we can do here is we're going to go ahead and integrate in terms of d of r. And when we do that, we're going to get r change of temperature over our, this is our temperature gradient over our radial distance. And then we are going to add a constant. We're going to add a constant 1 to this. Now, something that we can do here, remember constants, it doesn't really matter if they're positive or negative. So I'm going to shove this over to the other side and I'm just going to keep it positive. And we're going to set it over, we're going to set it equal to this, to the, what is it? We're going to set this equal to our, our radius times our temperature gradient. And then we're going to go ahead and separate this and just look at our temperature gradient. And then I'm gonna go ahead and integrate both sides. And now this is where we're actually gonna get talking here. So what are we gonna integrate this by? So I've made this cylinder over here. Sorry, this is left over from my notes. So I have this sort of cylinder over here, and I have this inner radius R of 1, and I have this outer radius R, we're just gonna call this R naught. And what I'm also going to say is that R1 is probably associated, or the inner radius is probably associated with an inner temperature. And we have the outer radius, which is associated with a outer temperature. And we are looking at heat flow only in the radial direction. And what we're trying to do is come up with an equation for us to sort of rationalize this relationship such that we can find a temperature at any point in between these two. So let's go ahead and continue with this equation. So we're with our integrals, with our d of t over here, we're going to obviously set this to our temperature inside and temperature outside. And this is a constant, so we know that it's just going to be temperature outside minus temperature inside. And this is set equal to our inner radius and our outer radius. And we're divided by r, which means that we're in terms of natural log. So this is going to be natural log, and this will be our the outer radius over the inner radius, just because you can say natural log minus zero. I mean, you can say natural log of the outer radius minus natural log of the inner radius, but I'm just putting in simpler terms so it's more compact. And then this would have a coefficient of C of 1. And something you might be wondering is, okay, so you have C of 1, why don't you have C of 2? The reason why is because if we are already doing a changes of, we're already doing integration and comparing outer and inner terms. If we think about it just intuitively, C of 2 is going to get canceled if we have a function like that exists. We were able to include C of 1 here because there was nothing really to compare with afterwards, so it's just going to be C of 1. But for this case, the C of 2 would just subtract itself out, and it's not relevant for the sake of the material that we're covering. So now we have now we can actually have a definition for C1. We can say that C1 equals the temperature difference of the outside and the inside over the natural log of the outer radius over the inner radius. Okay. So we have our relationship for C of 1 for the What is it? We have it for the outer and inner radius. What we need to do now is prove that this equation exists at any distance, because that's what we're concerned with. We're concerned with just t ambiguously at any distance. So this is where we're going to begin shifting uh, topics. We're going to, instead of just proceeding forward and assuming this is true, we're going to do something called making dummy variables and see if this calculus holds up at just t in general. So let's go ahead. I'm going to take the same equation and we're going to say it's C1 over R equals dt, or change of temperature over the change of radius. So I'm going to do the same integration, but there is one big distinction. We're doing this for the inner still, radius, and this is the inner temperature. However, what I'm going to say is that this is R and just R, and that this is T, and I'm going to put primes at the d of R and d of T. Again, so that we can just get it in terms of T and in terms of R. So when I do this, we get a different looking equation. We get T minus T inner equals C of 1 multiplied by natural log of R over R of I. So we get a much different looking equation. Now, what's even more different about this one is that T here and R here are not constants. They are instead variables. And so what that means is we can derive different meaning from them if we differentiate them. Sorry, I'll make sure I just move my camera a little bit. Okay. Sorry, I moved my camera a little bit. So let's go ahead and differentiate all of these terms. When I do this, t by gets canceled and we get dt over d of r. And I should say we're deriving in terms of radial distance. So this is a term that exists for us already. And now we can say that the derivative of this would be c1 multiplied by inner radius over r multiplied by 1 over radius, right? Yes, yeah, that's what it would be because this is just derivatives in respects to r for natural log in this case, and we're just moving c1 to the outside. And if we look, we can actually cancel these terms, and we get that dt over d of r equals c1 over r, to which if we look up here, that is consistent with our outer boundary terms that we have made. If you multiply this bar, you'd get the same thing. So this works. This equation makes sense for us intuitively. So how can we proceed? How can we make this analogous to a voltage term? Well, let's think about what voltage is. So I'm going to go ahead and write analogy. So we know that change of voltage equals current times resistance. Let's think of this in terms of thermodynamics. We know that change of temperature equals heat flow times thermal resistance. So we have our change of temperature term. We already have this term that exists. So let's go ahead and solve for Q, because if we have the change of temperature and we have Q, we should realistically have a term for R at that point. So we know what heat flow is using Fourier's law. I'm I'm so sorry for you. Fourier's law. We can say that Q equals negative thermal conductivity constant times cross-sectional area multiplied by the temperature gradient of, in this case, it's going to be temperature gradient of the radial distance or change of radial distance. So let's go ahead. I'm going to do the easy thing first. Area in this case, because this is a cylinder, is 2 pi L r. And I want to add I want to make sure that we understand. When I say R, I mean outer radius here. We're trying to do the entire cylinder, and this will be important for another reason later on, but this is the outer radius. So we can say that this equals negative k times 2 pi times the length times the outer radius. And if you look, we actually already have this term. So we can say that this equals C1 over, actually, so another big distinction. I don't want to get ahead of myself here. So we're saying that the area is in regards to the outer radius. So therefore, when we get the temperature gradient, this has to be where R equals the R outer radius. That has to be when the temperature gradient happens. And when we do that, when we plug in this equation, this is no longer C1 over R. This is instead C1 over the outer radius. So we can multiply this by C1 over the outer radius. And when we do that, we can cancel out like terms, or we can cancel out because it's being divided by that. And we get that Q equals negative K 2 pi L multiplied by C1. Okay, great. So we know what C1 is. We know that equals, I'm go ahead and write the rest of this. We know that this is multiplied by T, the original temperature minus, or the outer temperature minus the inner temperature, natural log of the outer radius and the inner radius. All right, so let's go ahead. We're trying to look for resistance, right? Let's go back to this voltage analogy that we've made. We have the change of temperature. So something that we can do is divide on both sides. We're going to go ahead and say Q minus T, the temperature outer minus temperature inner, equals negative K 2 pi L over natural log of outer radius and inner radius. All right. And now something that we can do is we can flip the reciprocal by multiplying both sides by negative 1, or putting everything to the power of negative 1. We get the temperature minus the inner temperature, we get natural log of divide this by K2 pi L. And then if we multiply both sides by Q, we get our expression. And what we can derive from this is we can actually get our resistance. Just making sure that this looks right. Yep. Well, to make sure I'm not missing anything. And this entire expression is our resistance, which is what we were looking for in this equation. So that is how we can derive an equivalent thermal resistance, analogous to circuits, by using this simple situation of deriving from our heat diffusivity equation.